Fine. So we wanted to continue and to complete our, well, I don't know if we'll complete, but to continue our discussion of BRST symmetry for the point particle and the string. So let me review where we had reached in the last class. We had that we were looking at the point particle action. We had that S was equal to, the action was equal to d tau x dot x dot x mu dot x mu dot by E plus E m square by 2 plus I b e minus 1 plus E b dot c. Okay, and using the general rules, we have the following rules for the transformation. So delta, the BRST transformation of x mu dot, or of x mean, was exactly as x transforms under a diffeomorphism, okay, but with c as the diffeomorphism parameter. So that was equal to, with our choice of i's, I epsilon c x dot. Okay. Then the transformation of E, the metric, you remember, was was similarly, it was delta E was equal to how E transforms under diffeomorphism. But you remember there were two parts to that. There was the part because it's argument transformed, and there was the part because it was one form. And we worked that out last class, and we got I epsilon C E d by d tau. Right, the part where the d by d tau hits the E was the transformation of coordinate, and the part where the d by dt hits the C was the transformation of the index transformation. Okay, as usual, we had delta B is equal to 0. We had, as usual, we had delta of B is equal to B. This was just the general rule. And then we had delta epsilon. Thank you. Thank you. Thank you. Thank you. And delta C. Now this I don't think we worked out last class. But I'll leave it as an X. You know, we had the general structure. It was C, C with an F. Now our F was the structure with the delta functions. Okay, you just have to plug that in. Okay, so the two C's were labeled by two different points. We had, you remember, the general structure was. Maybe we can just work it out. The general structure was, if somebody has it, in the general form, was there an I by 2? F alpha beta gamma C beta C gamma? Yeah. And please help me with the sign. Okay. And let me, and please, if somebody also has it, what was, what had we worked out for F gamma alpha beta in our particular case, the thing with the delta function? Oh, in fact, I have it. Yeah. Yeah. Okay, I'll just copy it from Kuczynski. This was delta of gamma, his gamma minus, gamma minus alpha, and then this was d by d gamma of delta of gamma minus beta, minus delta of gamma minus beta into d by d gamma of delta of gamma minus alpha. Okay, excellent. Now all we have to do is to plug this into this general formula here. Oh, what's wrong with this? Okay. So each of these beta and gamma involves a sum. The sum is an integral. Okay. So we have delta c of tau. C in general was labeled by C in general was labeled by what? There were as many C's as there were yeah, no, but in the general structure there were as many C's as there were infinitesimal gauge transformations. Right? C was an infinitesimal gauge transformation parameter. So this is the infinitesimal gauge parameter, so this was the C gamma. So we'll just replace gamma by tau. Yeah. Okay, so delta C gamma is equal to I by 2 integral d alpha d beta. Yes. Okay. Delta of tau minus alpha d by d tau delta of tau minus beta minus delta of tau minus beta d by d tau delta of tau minus alpha. And then what we have to do is to multiply this by C of beta, C of gamma, C of, alpha, C of beta. Okay, so now we just have to do these integrals. So in order to do the alpha integral, that sets alpha equals tau. So we've done this kind of thing before. That sets alpha equals tau. So we just replace alpha by tau. So that does nothing here, right? Because there's no, that just sets this. Okay, let's do it one by one. So it's I by 2. The first term is d beta, this d by d tau of delta of tau minus beta, and then c tau c beta. And then there's a similar term, so let's work this first term out. So that's I by 2. Now we just integrate by parts. So that becomes d beta delta of tau minus beta with c dot of tau, c beta, with a minus. Okay. And then we said use the delta function to do the beta integral. So that becomes c dot tau, c tau. Okay, so that's minus I by 2 c dot of tau, c tau. Okay, the other term will give the same thing. Now, there are two terms, and the other term will just cancel the two. Okay, and so we get, if we move the c dot to the right of c, the minus goes away. So we have delta c is equal to I at I c c dot. Okay. So for this point, if we work out the general structure of the BRST rules for the point particle example, this is what we get for the BRST transformations. Is this clear? This term? No, the action just was epsilon b dot c. Sorry, what? No, no, this is the ghost action. Sorry, what?
This was the term we derived
last class. Yeah. Yeah. And this is the term, you remember we said that Polchinski had it wrong first. This is that b dot. There were two terms. There was a C dot term and an epsilon dot term. And they combined together to give a B dot.
Last class did you do integration transform? It started with B.
Probably.
B times something.
Well, let's see. So what's yes?
Yeah, we have to take the derivative, transfer the derivative on the delta function.
That's right. There was some stuff. There were two terms, one of which. Yeah. Okay. Okay. Let's continue. Fine. So now this is the action that we had, and we could proceed with this. However, when we actually the analog of what we did with the string was that we didn't have this term. Because when we worked with the string, we actually used the, we didn't exponentiate the delta function. We just used the delta function to set e equals 1. If you have a delta function e equals, setting e equals 1, you have an integral over e, it's a bit of an overkill to use it, to keep it around, right? Okay. So now what we're going to do is to actually process both the action and these transformation rules to get rid of capital B and capital E. And little e, sorry. Okay? So what do we want to do? Of course, what we want to do is clear. We want to do the capital B integral. Okay? We want to do the capital B integral, and that will determine little e. We'll set little e equal to 1. Okay? And we want to see what happens to these rules as we proceed. So first, okay, so the first thing that we do is what happens when we set, when we do the capital B integral, gets rid of this term and sets e equals 1. So what happens to the action once we do that? The action is just d tau into x mu dot by 1 plus m squared by 2, okay, plus b dot c. This is the reduced action after we've done these two integrals. Okay, that's getting sort of familiar sounding now. This is the action we had just in the e equals 0, e equals 1 gauge when we looked at the point particle. It's the analog of what we're going to do in the string, right? It's going to be like the conformal gauge. Eta mu nu set to be conformal gauge action. Okay, the only difference is that in addition to this, we have the b dot c. What's the analog of that with string theory? It's the BC system. The analog of this is going to be the conformal field theory of the x's. And the analog of the b dot c will be the conformal field theory of the BC system. Okay, now this is what why I'm doing this point particle in so much detail, because it makes the structures, the parallel to the string, very clear. It's useful to do this once for the point particle, and then we'll very quickly rush through it for the string. It's more algebra, but the same ideas. Okay. Now let's keep going. When we work with this reduced things, what happens to these transformation rules? You see, some of these transformation rules, they change. Like for instance here, this doesn't change. What about here? Well, here we'll just say e equals 1. But there's something here. There's a b here. What should we do with b? Okay? Well, there's an obvious guess. In fact, it's more than a guess. It follows from Schwinger-Dyson equations. And the guess is that you replace this b by what it would have been with the e equations of motion. See, the original action had two variables that you're getting rid of. There's b and there's e. The b equation of motion sets e equals 1. But the e equation of motion, well, let's look at what that is. The e equation of motion of this action here is what? It's x mu dot with a minus plus m squared by 2 plus ib plus b dot c is equal to 0. Okay? And therefore, it tells you that b is equal to minus I, oh no, plus I. So IB, so minus IB on that side, and then I multiply everything by plus I. So plus I, let me just say that minus IB is equal to everything that's here. So B dot C plus M square by 2 by 2. Did this also have a by 2? Sorry, this also had a by 2. M square by 2 minus x mu dot by 2. Okay, that's what you'd get from the E equation of motion. And so what you might guess, so we're going to guess this and check. Okay, what you might guess is that there is an invariance of this action. This thing here, I didn't explicitly check it for you, but it follows from the general procedure that we talked about. But this is an invariance of this action. Okay, now the proposal is that this reduced action has a reduced invariance. Okay, and the invariance is delta x mu is equal to I epsilon Cx dot delta E. Oh, but there's no delta E, so we don't even have to worry about it. Delta B is not there.
Neither delta T.
No, neither delta B. So little delta B is equal to now I epsilon times B dot C plus M squared by 2 minus x mu dot by 2. It's a complicated thing. Okay? This was a symmetry of this action off shell, and exactly, exactly. So now, but this will be right. We will take this and check that it's also a symmetry of this action. Yeah,
Why is it checked? Is it not true that if you have an when the fields are off cell, this corresponds to another symmetry?
Yes.
Therefore, if you put fields on cell, this analog of this corresponds. This is just you are putting them on cell.
Yes.
It has to be a symmetry. Is it a set or?
No, it's yeah. So let's see. So let's see if we can make what Indranil is saying into a proof. Yeah, it probably. Let's first look at it classically. Was it obviously true? Probably obviously true. Probably obviously true. Let's try to see if we can look at it structurally. So what did we have? We had some action as a function of two kinds of variables, alpha and beta. Let's say alpha are these variables that remain, and beta are the two variables that we've integrated out. Okay. Now, what we had was that there was a symmetry of this action. So delta alpha is equal to delta alpha of alpha and beta, and delta beta was equal to some delta beta also of alpha and beta. Alpha and beta. For any alpha and any beta. Okay. So what that means is that if we took this action and we varied it, so let's say it's the Lagrangian, okay, integral dt. We took this the action and varied it, we would find that the action of the Lagrangian we vary it with respect to this, and we find that, okay, let's ignore possibility of total derivative for a moment. So just action, Lagrangian, same thing. So delta L by delta alpha plus delta L by delta beta, where this delta alpha and delta beta were these particular quantities, okay, was just identically equal to 0. This is what it means for it to be a symmetry. Now, what we now want to check is that if we vary just the alphas, what is important here? What is important, I suppose, is that the betas are completely determined by alphas, right, by equations of motion. At least in this case, that's true. E was 1 and B was something completely determined in terms of the other guys. So in this case, what we've got is some equation of motion that, without any recourse to initial conditions or anything, just determines the betas in terms of the alphas. Okay.
The counting, as long as the counting will work, the number of independent variables you have, you want to eliminate two variables if you have two equations.
If you want to eliminate two variables, you have two equations. Yeah.
If they are independent, then
Right. Well, let's see. Let's say that at least it's true for a moment. Maybe we can generalize that on the equations of motion tell us that beta is equal to some beta of alpha.
For beta equation of motion, this del alpha, del and del beta will be 0, right? Yes. From the equation of motion.
From the equation of motion, del L del beta will be 0. That is correct.
And
That
therefore, del L del alpha, this first part will be 0.
right. So now what you are saying is, now suppose we restrict to this particular set of configurations such that the beta equations of motion are obeyed.
Yes. Then alpha will be
Then alpha will be a symmetry. Right, very good. Because we just vary the alphas in this appropriate way. And this is 0, but this was 0 anyway because the equation of motion. Yeah. So structurally it's sort of clear. I agree. It had to work. I agree. Okay. But just to check that I've got the algebra right, that everything is working. Yeah. I'm going to check anyway that this is a symmetry.
there will be like epsilon equal to
Epsilon. Thank you. Epsilon c theta. I'm going to check anyway that this thing is a symmetry of this action. So let's just go ahead and vary. So what about the first term? So in the first term there's a 2, but there are two places, so the 2 cancels. So delta S is equal to the first term d tau. Let's take an I epsilon outside everything. Okay. So then there will be an integral C, and now, oh no, x mu dot, there will be one x mu dot, and then there's one variation, which is C x mu dot dot. Right? Okay, that's the first term. Variation of the second term is of course 0, and variation of the third term is, well, there's complicated stuff. Right? There's first the variation because of B. So now for the variation because of B, let's write it as B C dot. Okay? So minus B dot C plus m squared by 2 minus x mu dot by 2 c dot. Okay, and for the variation of the second term, we'll continue to write it as plus b dot times c dot, the whole thing, dot. Why the whole thing dot? Because the way I've
For the c there will be no dot, right?
You're right.
Otherwise there will be second derivative of c which we can't get rid of.
You're right. Okay, so now we have to show that this whole thing is 0 up to being there's a total derivative. Okay, so well, let's see. Let's see how this goes. This term, this was x dot by 2, and this c, and combine that with this.
Yeah.
Presumably that gives a total derivative. So let's try that. So let's take this term and this term. Okay,
Yes, yeah.
just the sign. No, minus and minus plus. Thank you. Okay, so this, what I'm claiming is this whole thing, that this term plus this term is d by dt of half d by dt of c x mu dot x mu dot.
Second term b dot c works because of phi and
B dot c works because of yeah. Okay, first let's look at this term. Let's see that this half d by dt c, that's the c dot here. And then when this hits the x dot, there's x double dot.
Yeah, there are two ways it can hit. One of the x dot comes out and the other hits it.
Yeah, and what about this extra c dot here? Wait a minute.
Oh. No. There's no c dot over there. So first time the derivative hits c, which gives us that term, and the other time the derivative hits cx mu dot with the other x mu taken out. Oh, I'm sorry.
No, something's wrong, right? I mean, there's some signs issues here. I'm sorry, just let me just open this whole thing out. That is x mu double dot c plus x mu dot squared c dot,
Yes.
and here we're getting
This is the first factor by 2.
plus
c by 2 plus
x mu dot
Yeah.
the thing squared c by 2, and that doesn't look good, right? Had this come with a minus sign,
Yeah.
it would have been perfect. So we messed up somewhere on sign. Let me let's check what Pulchinski has. He has I epsilon minus plus is plus b c dot. It's plus b c dot. Now where did that come from? Just right. let's see. There were many mistakes in what Polchinski had in this part. Unfortunately, I don't have the second edition. We didn't make much of them. Does anyone have next edition of Polchinski on you? The latest edition? Yeah, it would be nice just to check his transformation rules. I'm sorry about this. I remember when I last taught this that I got very confused because he had many things wrong here, and just trusting your own algebra was more. But it's irritating that my own algebra is not doing something consistent. It could be that this sign is just wrong. Yeah. That will fix it, right? Yeah, if you could, I'll tell you which section to go to. Yeah.
This one I want.
No, that sign doesn't do anything over there.
Well, if that sign,
This is the wrong sign you have written.
the B dot C?
Yeah, exactly.
Okay.
Confusing.
Huh. So I just flip the sign?
Yeah, it will be minus.
Minus. Thank you. That will fix everything, I think. Okay. So,
But in del B that was minus. Del B it was B dot C, right? What
The-
you have written? That will be minus.
this has a minus. Minus B dot C. But this is okay
The action is not okay. Yeah, action is now okay.
with a minus.
Yes.
So then this also had a minus. Is this right? Okay. I'm sorry. I'm sorry about all of these. Last time when we derived it, we have a plus. I can't remember. We had B dot EC with a plus. So that was the root of our problem. We derived it with the sign wrong. I'm going to go ask you to go back and check that sign. Okay, I'm sorry. It'll take too long to go and get that sign right. Somewhere I messed up on this sign. This is the root cause of all our trouble. Okay. So minus, and this guy comes, you say, with a minus. Now let us see if things are better. This term came from, we took plus, because we took the B dot, we made it B C dot, and in the transformation of B, Indranil wants us to have a minus here, but this remains there. And now the relative minus works out for this thing, and so it's this total derivative.
Last one, what about the last one?
Yeah, it's now this, and that's what we want. Thank you. Okay, now, but just if we look at the x dot, x c, these terms, this plus this now is total derivative of this. Okay? Because the other part, the right factor of 2 to make that work. Okay, so this term and this term we dealt with. Now let's look at the other terms. The term that is m squared c dot, of course, is total derivative by itself. And now we've got these extra terms, which are minus b dot c c dot minus b dot c c dot. Okay? So minus b dot c c dot minus b dot c c dot. And what is this?
B times C square.
The c square is 0.
Yes, so B times C square and B times C square.
So b dot times c square is what you want to say, right? No, b times c square.
No, the two times right.
B times C square
b dot times c square, which is 0, and a b times c dot. Yeah, the point is that this is you see, d by dt of c square is equal to c dot c times 2, but this was 0 because c square was 0. Okay, so this quantity here.
No, it's actually c dot plus c dot c.
Plus.
Which is again identical.
Ah, you're right.
That's-
You're right.
that's-
You're right.
Otherwise, every c dot
Would have been 0, which is too much. Yeah, you're absolutely right. Let's see. Why? Where is this? Just give me a minute. Sorry, could you also check
Yeah.
everything, please? Because one sign would fix it. C dot, this was good, and did we do this correctly? Minus b dot, we didn't do it correctly because there's an epsilon.
The anti-commuting epsilon.
Plus.
Yeah.
Okay, so this was just 0. Okay. Okay, so there was no cleverness needed. It was just this total derivative business, and then 0. Okay, so now we've got consistent set of rules. Right? We've got a BRST symmetry, we've got an action, it's consistent. I'm sorry for the mess up. Somewhere I made a mistake with a minus sign here. I'm sorry for that. You can track it down, I hope. Okay, fine. So now that we've got everything nice and consistent, let us, we could have tracked down the original mistake by checking that this set of rules was a symmetry of that action. We should have done that exercise. Okay, if we'd done that, we would have tracked down that mistake. I'm sorry, but somehow. Okay, here we go. Okay. Okay, I leave to you the other checks. Checks like that q squared is 0 using these rules. Of course, now you will get it 0 only using equations of motion. Okay, you will find that when you act q squared, it's in this formalism.
No, for this restricted action, the q square wouldn't it be identically, 0 whether or not we take on-shell or off-shell configuration?
I don't think so, actually.
I think we have to impose.
I think it's only on shell. Well, let's actually just check. You see, because this is a complicated thing.
Yeah.
Let's actually even roughly check. We'll act with this, and then we'll act with it again. Okay. So here we will get how. Yeah, that part is probably just okay, right? Because so how will it work even approximately? How did it work abstractly last time? So we had delta phi alpha was equal to, what was it? Delta alpha. Yeah, delta phi, C alpha delta phi. Delta alpha phi with an epsilon. And then we did another one. We did C alpha epsilon 1, this was, let's say, C alpha, and then we did epsilon 2, this was delta alpha 1, let's call it, delta, no, just delta alpha. Yeah, delta alpha 1, C alpha 1 epsilon. Then there was delta alpha 2, C alpha 2, delta alpha 1 of phi. and what was uproof last time? Sorry. So this was epsilon 1, epsilon 2, C alpha 1, C alpha 2. We do it. Thank you. That was the point. Okay. And then there was a variation of C, and both those terms cancelled each other. Right? Because this F was anti-symmetric because of the two C's. So there was an F alpha beta. And the variation of C also had an F alpha beta. And those two terms we checked last time, right, with signs. But those two terms cancelled. That will continue to happen because the C and X variation are the same as the off-shell things. Yeah. The B variation, I suspect, will be the, and this will also continue to happen. This is just the thing that used Jacobi identity, and that is unaffected by this integrating out procedure. It's this thing that will become complicated. Right? Last time it was very trivial because delta B was capital B and delta of capital B was 0. Okay. Now we're going to get some complicated stuff, and that complicated stuff will be 0 by equations of motion.
Yeah.
Okay, but I'm going to leave you to check that. Okay, great. Great. So now we've got these BRST transformation rules.
It has to be 0 by equations of motion because it's sort of gauge fixed now. It's partially, the partial gauge fixing has already been done. So the equations of motion
have to be invoked somehow.
at some point, right?
Yeah, I think that's probably right. I need to think through clearly why the logic, but certainly I think just algebraically certainly, and there'll be some logical reason for it. Okay. Now, what I want to do now is to take this action with this BRST symmetry and work out the BRST cohomology. Okay? So what is the quantization of this system? Well, the quantization, there's one last thing that we need to do, and that is work out the charge, the BRST charge that generates these transformations. Okay? So in this point particle example, let's work out everything completely, and then we will be more loose when we work with the string. Okay, so let's work this out by Noether procedure. We've got a transformation rule, and I want to find the current, the conserved current corresponding to this transformation. Okay, so what is the rule? We just put this in, but make our epsilon a function of t, and find the coefficient of epsilon dot. Okay, and that will be J0. Of course, in general, that's J mu, but here it's 0 plus 1 dimension, so that's the charge. Just work out the coefficient of epsilon dot after we put this in. Okay. So we've already just checked. That if epsilon was a constant, it's a symmetric. Okay. Now, where in that check so now we just need to look at the epsilon dot. So if we put this in, there will be one term here from here. Okay? So let's carefully get that straight. So there will be one term which is I epsilon dot. That's the dot appearing in here. Then Cx, x mu dot. I epsilon dot C x mu dot divided by 2, but the by 2 has gone because there are two variation terms. Okay, so that's one coefficient of epsilon dot. Right. Now, then there is the coefficient of epsilon dot that comes because we put, of course, nothing from here.
Yeah, from B dot.
From B dot or from C. Okay. So let us write this whole thing. Let's take the C term first. So now we have a choice. How are we going to write it? So let's write it like this. Okay, so if we write it like this, then in the variation in B, there was no epsilon dot, just epsilon, whatever. But in the variation in C, there is an epsilon dot. So in the variation in C, we get plus B. Now,
Minus, so epsilon will.
Put an epsilon dot here. I'll take that later. The I is always there. Plus epsilon dot, then CC dot. Okay, so that is equal to I epsilon dot into C x mu dot x mu dot. And let me take the C outside also. I epsilon dot C x mu dot plus, so I've taken epsilon through B and I've taken C through B. So no sign, B C dot. Where?
In the first above line, you took epsilon dot.
Yes.
Del C, differentiation of del C with respect to T is needed. One term is this one. The other term is acting on C dot, which is 0.
Sorry, I didn't understand. Wait, you're talking about just the this plugging in here?
The last term is B times
C dot. Yeah. I'm looking at only the epsilon dot term. Because everything else we've seen is 0, right?
Oh, you are just keeping the epsilon dot. Yeah, then I am thinking.
Yeah. Okay. So now this quantity here okay, let's define this whole quantity here as this whole quantity here we'll call H.
When you are taking epsilon dot through B, taking epsilon dot common here. When you are taking epsilon dot through B, are you not taking
But I'm also taking C through B.
C through B?
I took the C out here. Yeah. And just, was there an M square? Kulchinsky also has an M square somewhere. Did I mistakenly drop that? Just one minute. I'm sorry for just let me get an M square. I'm sorry, give me 1 minute. I know. I'm doing something wrong. It's this somehow this business that there's also the total derivative term there. And just a minute. Yeah, it does, but just let me get the logic. Yeah, it's that I'm missing. Where is the m square cannot come under order?
Because m square is there is a total derivative. It was there with c dot.
Okay, excellent. So that's just the idea. When we threw away the but here no. I'm sorry, just a moment. That's perfect. That's the m squared by 2. I just need to figure the logic out. What is that? You're right. That's the c dot. That's placed. Exactly. So we were too cavalier. Okay. Here, in the variation of B, we said in the variation of B, there is just an epsilon, so there's no epsilon dot. But in the variation of B, we threw something away because it was a total derivative. So it was a total derivative if epsilon was constant. But if epsilon was not constant, that variation would not be a total derivative and would instead give you an epsilon dot times C. Okay, now let's get the sign right. That's the next step. Okay, so in this variation, we get C dot times I epsilon. So if this sign is correct, we've got m squared by 2 I into epsilon dot because of with a minus sign, because of the integration by parts, times C. Do you agree?
And a similar logic would also apply for the other total derivative term, this C x mu dot x mu dot.
Yeah. C
Or by 2, I think
that's
that's the term.
the term. Okay. Let's do it really carefully. Let's do it really carefully. I agree. I'm sorry. This is stupidity, but let me just. I'll just work the whole thing out again. Okay, we have this whole thing here. I'm just going to redo it. I'm just going to add the terms with epsilon dots, yeah? And just be very careful. Okay. So there was this. Then what additional terms do we have with epsilons? The additional terms we have with epsilons, as we've said, is these terms, right? The additional terms we had with epsilons are plus I epsilon dot C x mu dot x mu dot. That is the explicit epsilon dot terms. Okay? And we'll just put in an epsilon here. Epsilon, this is all a function of time. And there was this additional epsilon dot term. We'll make this minus this with an epsilon. Which then of course we're free to integrate by parts. So there's an epsilon here, and this. Now is this, I'm sorry. Yeah, sum of these 4 terms plus this is the full variation. Do you guys agree? Is this good? Let's see. Well, here all I've done is take B. Yeah. What happened to this sign? I had taken epsilon to the right. So with this epsilon here, then a plus. Okay. Yes. Okay. Excellent. Thank you. Okay. Now what we will do is now carefully take total derivatives including epsilons. Okay. So as we said, we want to take this term, and this term, and write it as a total derivative plus an epsilon dot then something. Okay. So I'll just write out all the terms. This is epsilon times x mu dot into into c dot x mu dot plus epsilon times x mu dot into c x mu double dot, okay, minus epsilon times x mu dot by 2 times c dot, okay, plus epsilon dot times c x mu dot x mu dot. Okay. Now let us write this whole thing here as d by dt of epsilon c x mu dot plus something by 2. I'm clearing this, and then there is this plus epsilon dot by 2 c x mu dot x mu dot. Okay, because these three terms, as we've seen before, are just the derivative of this, and then half of this term goes into this. Okay, so what remains is this. Okay, so this is part of what remains. Very good. Then there is the next term, which was the term that that you pointed out, which was plus epsilon m squared by 2 c dot. So this was total derivative minus epsilon dot, so this is the same thing as minus epsilon dot minus m squared by 2 epsilon dot c. Okay, this remains. And there was the other term that remained, which we probably got right, but let's, yeah. Here it's now just the explicit epsilon dot, because the other terms cancelled. Right? So the last term is minus epsilon dot into b c c dot. Okay, so the full thing now is epsilon dot into c, epsilon dot into c into x mu dot by 2 minus m squared by 2. Oh no, c has to go, no, correct, epsilon dot c. So minus m squared by 2, and then here with a plus b c dot. All good? Okay. Now this whole thing I'll call the Hamiltonian of our system.
Including the c, right?
No, not including the c.
Oh, not including the c.
Not including the c. You see, this part is the matter Hamiltonian, and this part is the, well, this part of course is just 0. You see, by equation of motion,
Yes.
by the equations of motion, this thing here is just going to be 0, because the equation of motion tells us both b dot and c dot is 0.
Yes.
So this part is basically quite trivial. Okay, this part is basically quite trivial, but this part here is the matter Hamiltonian. Now, why is it the matter Hamiltonian? Are we getting the signs right? That is the next tricky question. Firstly, let me see whether he has. Oh, wonderful. He has the same signs as us. Okay. Okay. Yeah, he has the same signs as us. Okay. And Polchinski's logic is this. Look, I am clearing this part. See, in Minkowski space, the Hamiltonian is p squared by 2 plus m squared by 2. Yeah, because we're doing e to the power minus s. Okay, anyway, p squared by 2 plus m squared by 2. M squared will continue to the potential. This is a kinetic term. Okay, so what we call the Minkowskian Hamiltonian is p squared by 2 plus m squared by 2. P squared is of course x mu dot squared by 2 with our Lagrangian. Okay, so this would come to x mu dot squared plus m squared by 2. Go on.
I take this action.
Yes.
I don't know where it came from.
Yes.
Fields are x, b, and c.
Yes.
And then this transformation is a symmetry of this action off-shell or on-shell.
I mean, it is a symmetry off-shell. There's no such thing as a symmetry on-shell.
This is what I am trying to ask this question. Is it that this action with this transformation law,
Yes.
without using any equation of motion for x, b, and c,
Yes.
will just be a symmetry?
Yeah, that's what we've checked. Right? We just checked that the variation of the action was 0.
That is the only thing that required
Equation was q square is equal to 0.
q square is 0, which is
Yeah. Okay, that is a symmetry. There is no meaning for something to be a symmetry on shell.
exactly.
Yeah. Okay, great. So you see, p squared in Minkowski space was x dot squared plus m squared. Do you see that the plus is important here? Because this plus is a plus in Euclidean space, which goes over to a positive potential in Minkowski space. And Hamiltonian is p squared plus potential. Okay? So now you might think, okay, we're getting a minus. This is a plus, so there's a sign mistake. However, this x dot was a Minkowskian x dot. In Minkowski space, we got x dot squared by 2 plus m squared by 2. So you change this x dot to the Euclidean x dot, that picks up an extra I. That I squared gives you an extra minus 1. Okay? So up to an overall minus sign, this guy is the Hamiltonian. Okay? This guy is also, in some formal sense, the Hamiltonian, actually minus of the Hamiltonian of the fermionic system, but it's just 0 in this case. This is very trivial. We're going to have the analog of that in the string. Okay? So this quantity here, which was just this x dot by square minuses, is up to a minus sign. It was 0 because first order, exactly. Just that both b dot and c dot are 0 by equations of motion. I'm saying
First order in time, therefore it was 0. You calculate the Hamiltonian, it is 0.
yes, that if you calculate the Hamiltonian just from this, you'll get 0. And I'm saying this quantity by itself, yes, that's right, and this quantity by itself on shell is 0. So that agrees with it.
That is that in strings case, you are saying that will play some role.
That will play a role, yes. Okay.
It's first order in time as well as linear. That's why it's 0, right? Otherwise, for example, the Dirac Hamiltonian is not 0.
No, but this thing has a time derivative. If there was a term without a time derivative, that would not be first order time. And the Dirac, that is homogeneous. First order and homogeneous in time derivative. Yeah. Okay. Excellent. So now let's look at this quantity here. Okay, so this quantity here is the Hamiltonian, so we'll just write it as Q BRST, and we don't care about the sign. So Q is equal to C times H.
Oh, yeah.
Okay, now we're in business. So now that we have this nice Hamiltonian way of thinking of the problem, we can easily figure out the cohomology of the BRST operator.
So,
Yes?
this is probably just semantics, but why is this Q called a Q BRST now? Because the original BRST symmetry is no longer present in the current form of the action. We have integrated out some.
But you see, we continue to have a fermionic symmetry which squares to 0,
Yeah.
and which is the original BRST symmetry once you impose equations of motion.
Yeah, I mean,
It's
yeah,
just
I mean, there's the
No, but imposing the equation, that's fine. You see, the only thing, see, in the original form, we had determined that we would only allow ourselves to consider states that were in the cohomology of that BRST symmetry.
Yes.
We must continue to do the same here.
Yes.
Because the only allowable operators were those that were in BRST symmetry of that original theory. Now, you only have those insertions, then you integrate that out. But you should only look at the cohomology of that operator, of that Q operator. So you have to continue to do that here. So that's the important thing. That the BRST symmetry was playing the role of determining which were the allowed states. And we'll continue. This will continue to play the role of determining which are the allowed states. Okay? So now we'll try to figure this out. So firstly, we want to think what is the Hilbert space of the full system.
Even for Dirac Fabian,
Uh-huh.
take Dirac Fabian, don't gauge fixed stuff. Tau is your curve parameter,
Yes.
and then you calculate the Hamiltonian.
If you calculate the Hamiltonian in 4 dimensions, you won't get 0.
You are going to get
Non-zero. Because there is a d by d tau, but there's also a d by d xi term. And the d by d xi term will give you a non-zero Hamiltonian.
it will give you some non-zero. If you don't gauge fixed stuff,
Gauge fix with
tau, you have this reparameterization.
with Dirac Hamiltonian. So you're thinking just of ordinary Dirac equation? There's no reparameterization.
No, that you have fixed, right?
What?
Ordinary Dirac equation, the way you write with dt,
Huh.
you have fixed everything.
Yes.
So that will be non-zero, right?
Yes. Yes.
But if you start with the ungauged fixed person,
What do you mean by ungaged expression?
write down the diffeomorphism invariant.
So with the spin connection and all of that. Okay? Go on. Yes.
And then you calculate the Hamiltonian in tau, which is the curve parameter.
You calculate the Hamiltonian in and tau is what?
In free particle, let's say you had d tau,
Uh-huh.
which you could have gauge fixed to t,
Uh-huh.
and then you could have calculated Hamiltonian,
Uh-huh.
which will be non-zero.
Wait, are we doing one dimension or more dimension?
First, in let's say one-dimensional free particle.
Yes.
This is the action where you have d tau,
Yes.
and these derivatives are with respect to tau.
Yes.
Now you can do two things. One thing is gauge fix tau to t,
Yes.
and then get a Lagrangian, and
Well,
then calculate
Oh,
Hamiltonian.
gauge fix e to 1 like we've done here.
Yes.
And get a Lagrangian and you get a Hamiltonian and it's generally non-zero.
Yes. So if one example is fix tau to t, is a gauge fix tau to t, and then calculate the Hamiltonian that translates in t.
Yes.
That will be non-zero.
Yes.
But in this quantity, if you calculate the Hamiltonian which translates in tau,
Yes.
that will be
Well, at this stage it's non-zero. It being 0 will be one of the conditions.
one of the conditions.
Yes.
Right. That in tau that will be 0.
It will turn out to be 0, but it's not yet 0.
Not yet 0, but it will turn out to be 0 by the one that translates in tau.
Yes.
So now let's go to the field theory
Yeah.
with the fermion.
Yes.
When you gauge fix your curve parameter to t, you get the usual.
Wait, no, gauge fixing what to t? You just say a coordinate to what? I don't understand what are the two things you want to gauge fix.
So let's write down the Dirac Lagrangian.
In how many dimensions? 4 dimensions, let's say.
4 dimensions.
Okay.
And in totally diffeomorphism invariant, right?
We've got it.
And then in that you have a parameter which is called d tau. You have
Out of your 4 coordinates, one of them is tau.
tau,
Okay.
and then you want to calculate the Hamiltonian which translates in tau.
Yes.
And then
The-
what would it be? Because in free particle case, the translated in tau that turned out to be 0, right?
Yeah, yeah, this will in general not be 0. See, because whatever your tau is, you've got some manifold. You've got some slicing of your manifold. That's lines of constant tau are is your slicing. And translating in tau will be moving from one slicing to the other.
Translating in tau will be from one slicing to the other, yes.
So it's not 0. It does something non-trivial.
So in free radical, why did it turn out?
In this thing? What do you mean? In the one-dimensional case?
Yes.
Okay.
Sorry. I am asking this for the reason.
Yeah, but let me quickly give you the answer.
Yes.
The answer was that this action was diffeomorphism invariant in tau without involving a metric. You see, to start with, let's take the Nambu-Goto action. It had a diffeomorphism invariance in tau without transforming a metric. Okay, so tau was really topological direction. There was no tau. Okay. On the other hand, every action is diffeomorphism invariant in tau if you also transform the metric. But that's not what we're doing when we do field theory. We change tau, but don't change the metric.
Then this is not the usual kind of diffeomorphism.
It's not, yeah. So shift in tau, when you ask for shift in tau, you ask for what happens without also changing the metric.
This is non-trivial.
This is non-trivial. Okay. If you also change the metric, you go to a different theory.
In field theory,
you go to a different theory.
only when your diffeomorphism in metric address. So if you have a theory of gravity, in which your
Ha.
metric is also changing, then it will be.
And here you are coming to the fact that the Hamiltonian in gravity is a constraint.
Okay.
Now we'll deal with it.
Then
Yes.
that will be the.
Then it's of course 0.
Okay.
Okay? But not in field theory.
Not in field theory because you have fixed your. I'll always say the metric is fixed.
Exactly, your
Not
metric is
what I want in the-
You've got a particular manifold, moving a coordinate moves you on that manifold. It's physical.
Maybe something.
Okay. Okay, great. So now what we want to do is to understand what is the, I'm sorry this has taken so long. Okay. No, it's good to have questions. It's great to have questions and helps me, helps everyone. Okay. So please continue the questions. I mean, don't stop the questions. That's what makes the class fun. Yeah. Okay. All of us learn from it. So, okay. So let's keep going. Okay. So we had this BRST symmetry as C times H. And now I want to compute its cohomology. So I first want to understand compute its cohomology in what Hilbert space? So what was the parent Hilbert space whose cohomology we want to compute? Well, it's the Hilbert space obtained by quantizing this action. Okay? I will shortly give you a little primer on how you get Hilbert spaces by quantizing fermionic path integrals. Maybe even the next class. A clean way of understanding that. But all of us have some intuition that this action here gives us a two-state fermionic system, right? At this point, I don't want to go through that. All of us know that quantizing B C dot gives you the two-state fermionic system. You can think of it roughly with the analogy of canonical quantization. What a normal textbook, or a textbook which is not as good as Pulchinski will tell you is, is that you just canonically quantize this, but you replace commutators by anti-commutators, and every student who is a serious student feels, well, where did this come? Yeah, this feels a bit too. There's a much better way of thinking of it, which we'll discuss. But at the moment, you've all seen that textbook explanation. You've all bought it when you look at the Dirac equation, for instance.
Einstein's constant, if it gives some social gives
Exactly. Okay, so you won't have trouble believing me that this will give you will implement the commutation relation B C dot, implement the commutation B C anti-commutator is equal to 1. You won't have trouble believing that, right? Okay, we'll understand exactly why this path integral gives this Hilbert space and so on very clearly, maybe next lecture. Okay, the transition from path integrals to Hilbert spaces in bosonic things, all of us have studied correctly following Feynman and Higgs. There's a similar small analysis that some of you have seen, I suppose, that you can do with fermions, but it's not done in standard textbooks, so I'll do it for you. So you can cleanly go from a path integral to a Hilbert space. I'll show you that very soon. But right now, let's just accept it. Okay, so what we've got is these two fermionic operators which square to 0. because part of what you get is also that B anti-commutator B is 0 and C anti-commutator C is 0. So B squared is equal to 0, C squared is equal to 0, BC is equal to 1. Okay? And that of course generates a two-state system. This is the anti-commutation relation of sigma plus and sigma minus. In fact, it's exactly the anti-commutation relation we encountered in the zero mode sector of the BC system for the string. And we understood exactly how to quantize it. So we have these two states down and up. There, by the way, we did it carefully because we did it through contour integrals. I showed you where the anti-commutator came about. I was not using some Bjorken and Untitled style prescription. Okay, okay, we did it correctly. In this quantum mechanics, we need to go through a similar exercise, which I'll go through. Okay, but at the moment, you won't have trouble believing that you get this down and up state, and we'll use the same conventions we had before, which is that B on down is equal to 0, B on down is equal to up, C on up is equal to 0, and C on down is equal to up. You remember we checked that this is what happens if you use. So that's the Hilbert space that you get from the BC sector. And the Hilbert space that you get from the X's, well, we all know. These are the 26, or the D, capital D dimensional free particles. Right? It's just the relativistic Hilbert space of D free of particle moving in D free dimensions. In relativistic Hilbert space of a particle moving in capital D dimensions. So that Hilbert space is labeled by P mu. So a basis for this. So P mu down up and P mu down form a basis for our Hilbert space. Okay. Now what I want to do is to compute the cohomology of this BRST operator. So the first thing I'm going to do is just compute the action of the BRST operator on our basis vectors. Okay. So first, Q P mu up is equal to what? Which is 0. Okay. So all up states are Q closed. That's good. Now let's look at Q acting on P mu down. Now the C part makes it P mu up, but there's also an H here, okay, which gives us which is equal to P squared plus M squared by 2 on P mu up. So now let's look at BRST cohomology in the up sector. In order to be in BRST cohomology, the up states have to be closed as well as not exact. Okay, all the up states are closed, so that's good. But almost all of the up states are exact, because almost all of these up states are Q acting on something. The only up states that
unless the moment it's on mass shell.
Exactly. So the only so BRST cohomology is, you know, states with P squared plus M squared equals 0 and P mu up are closed and not exact. Cohomology is those states that are annihilated by Q modulo equivalence classes of states annihilated by Q. Under the equivalence, Q psi is equal to psi plus Q alpha, where alpha is any state. Okay, so two states that differ by something that is Q on something are treated as the same state.
Similar to the definition we gave last.
Yes, same definition. Okay? Good. So in up sector, this is the cohomology. What about in the down sector? Well, in the down sector, it's even easier. Firstly, no down state is Q exact. How do we know? Because we just acted with Q on every state in the problem. And we never get a down state on the right hand side. So no down state is Q on anything. Okay? So in the down sector, anything that is Q closed is in the cohomology. And you see we get Q closed on mass shift. Okay? So P squared plus M squared equals 0. P mu down is also in cohomology. Now if you remember our ways of computing, our previous analysis of the Hilbert space, let's say any one of these analyses that we had right at the beginning of the class, we found that the Hilbert space was all P mu's such that P squared plus M squared was equal to 0. Here we've got the same answer except we've got twice that answer. And we've got one for the up and one for the down. And what's sort of going on? Yes. You remember when we quantized the particle right at the beginning of the course, we found that the correct Hilbert space, the Hilbert space once we impose the constraints, was P mu such that P squared plus M squared was equal to 0. You see that constraint from one way of thinking came from the E equation of motion. The Hamiltonian.
Is it all because when you had this axiom written, you had to make a choice that either you write BC dot or you might write minus B dot C.
Mm-hmm.
You need to make a choice for oscillation.
But these two things are equivalent up to total derivatives.
Up to total derivative. So, why is this symmetry? Is there no symmetry between B and C? Up to derivative.
Oh, sorry. Wait. Oh, well, no. There's no symmetry between B and C. Yeah. Why was there no symmetry between B and C? Because B and C, you see, it wasn't just the action. It was the actual role of the symmetry. If we took the symmetry, one way of saying it is if we took the action.
Action of Q in a different manner.
Yeah. One way of saying it is if we took the action before we did this last integrating out, the action with the epsilon, then there was an epsilon B dot C, not an epsilon C, B C dot. There was no symmetry.
There was no symmetry.
Yeah. And of course, B and C played a very different role.
They are actually different in all examples except in this particular one.
In this particular example, after finally gauge fixing.
Yes.
Okay? So if we just follow through right from the beginning,
Then there is no symmetry.
there was no symmetry, yes. And you really see that in this form of the BRST symmetry. The BRST symmetry is C times H, not B times H. Okay.
There was no symmetry.
They were never on equal footing. Yeah. Okay. So now do you see that what we've got from this complicated BRST quantization, what we got from this complicated BRST quantization, I toyed with the idea actually of presenting this right at the beginning of the class. But it's so complicated and this last part, it felt like it, yeah, okay, fine. Anyway, so what we get from this complicated BRST quantization is twice what we know is the correct answer. We know from many different points of view that was the correct answer. Here we're getting twice it. What's going on? So let's look at these two things once again. Both have the same cohomology, but in two very different ways. This guy here was the cohomology. There was never anything exact. This cohomology, this constraint came from closeness. Okay, this constraint came from not being exact. Now what does it mean? See, I was never allowed to insert one of these operators unless we were on Marsh. Right, because it's just not closed. Here, I'm allowed to insert any of these operators. Okay? I don't need to insert the operator only when p squared plus m squared is equal to 0. I'm allowed to insert it anyway, because our rules say you're allowed to insert any operator as long as it's Q closed. But we are guaranteed that the answer will be 0 if the state was exact. Okay? So now, if you do a calculation here, if you insert, one of these operators, you're allowed to do that. You'll get some answer. But the only way you get something non-zero is if p squared plus m squared is non-zero. So your answer, whatever you get for all insertions with these operators, would have to have a factor of delta of p squared plus m squared. If it's non-zero at all, it would have to have such a factor. Now the things that we're going to calculate will calculate scattering amplitudes. We're going to calculate various things, and this kind of quantity, as we will see as we actually do calculations, we'll see in a few examples, never arise in computations in quantum field theory. S matrices or correlation functions. In fact, for the point particle, in the point particle example, we could actually just compute correlation functions. It actually becomes even clearer. Off-shell correlators. Okay? In the computation of an off-shell correlation function, this quantity here, okay, this, we would point to this thing here, we don't need to be on shell. Okay? And this quantity, this can only give you a contribution when p squared was, plus m squared is equal to 0, and therefore can only give you a contribution which goes like delta of p squared plus m squared. If you put this insertion for arbitrary p squared plus m squared, you do the answer, you can only get such a contribution. So it would have to give you some contribution to off-shell correlation functions, let's say. Okay? Which have an explicit factor of delta of p squared plus m squared. But in quantum field theory, such factors never arise. There are certain analyticity properties of correlation functions in quantum field theory. You can have poles, you can have cards, but you never have delta functions like this. Actually, there's one exception. In 2 dimensions, you're allowed to have these delta functions. The kinematics are special, but outside 2 dimensions, this will never arise. So you might predict right from the beginning that although these states formally are allowed, if you compute anything with an insertion of one of these things, we know we're going to get 0 everywhere except p squared plus m squared equals 0. Perhaps it will turn out that we'll just get 0 everywhere. Because otherwise we would have got something which has this analytic structure that is not allowed in quantum. When we look at the analog of this for the string, I will show you some examples. Okay, there's some formal cohomology that is non-zero, but actually any quantities you compute using that will just give you 0. Just because it's the analytic continuation of other quantities that were 0, that you were allowed to calculate. You understand the difference between these two? This guy was closed only when p squared plus m squared is equal to 0. So you were not allowed to put any insertion except on that point. What? The lower one tells you can compute only on shell. This one allows you to compute off shell. You could do that, but I'm saying that there was an allowed calculation which was 0 everywhere else, and you'll see that it's analytic. So we'll be forced to be 0. Just calculation will give you, Feynman integral that's 0 everywhere, and so will be 0 here as well. So just analytic continuation will tell you that this answer is 0. Okay? So, although formally you get a cohomology that's twice as big, actually part of this cohomology is just trivial. The non-trivial part of this cohomology, the thing that will give you anything real and non-trivial, is just the downstates. The guys that were closed only on shell. Okay, I won't do explicit calculations for you with this point particle example, though it's sort of instructive to see. But when we move to string theory, I'll do a couple of explicit calculations just to show you show you this working. It'll become totally clear. You'll just get 0 everywhere, including on shell. Okay, so though formally it looks like the cohomology is twice as big as it should be, one part of this cohomology is just trivial and will play no role. So this is some fake, something to distract us. Okay? The real cohomology of the theory is this guy. Okay? Wonderful. So now we have thoroughly understood the point particle example. We've thoroughly understood the point particle example, and now we want to go on to the study of string theory. Okay. Any questions or comments before we continue? Okay. Maybe here I'm just going to write down a few answers, and I'm going to give you lots of exercises to check. The algebra is going to be very, very similar, though more indices. Okay, I'm going to write down a few answers, give you some exercises to check, and then if there's any questions that come up while you guys do these exercises, we can discuss them. Let me write all the point particle formulas on one side, and then I'll give you claims about the string world sheet answers, and you see if they sound reasonable. For the point particle, we had delta x is equal to I epsilon c x dot delta, but now we'll look at this gauge fixed form, the form we had on that side of the blackboard. So delta b is equal to I epsilon into minus half x mu dot plus half m squared plus bc dot, and delta c was equal to I epsilon by 2 cc dot x. Yeah. Okay. If you go through all the exercises we went through for this point particle, so what are the exercises you have to go through? Well, most satisfactorily what you would do is work out, use as the BRST symmetry, the gauge symmetry that you have to fix, diffeomorphisms and Weil symmetry. Okay, these two things. Then work out the BRST action for this full invariance with, of course, the gauge fixing condition once again taken to be g mu nu minus eta mu nu is equal to 0. Or it's some fixed metric, but let's say in a local patch, that metric is eta delta. We want to gauge fix so that we use diffeomorphisms and Weil symmetries to set the metric to be something fixed. But patch by patch, as we've discussed, you can set it always equal to delta mu nu. So let's work in that patch by patch formula. Okay, so what you would do would be to take your action, the action which is the off-shell action. Okay, so you would have integral square root g alpha beta del alpha x mu del beta x mu. Then you would have the gauge fixing for which you had a Lagrange multiplier. Okay, so you have some b mu nu g mu nu minus delta mu nu b mu nu minus delta mu nu, that is like the BA FA term. Okay, and plus you will have the BC system, the BC ghost system, the stuff that we worked out when we, you know, right? So it's this, the BP business, yes. BPC. Okay, though actually you would have it even before we did the, even before we did the integration out of that conformal mode. Okay, so we had the conformal factor. There was a term which was sort of like B mu nu delta phi and then B mu nu delta, some delta phi term, now I forget. Okay, sorry, just, I won't even say, you know, we did this, so this is what you get after integrating all the conformal factor. I'm saying if you do it most satisfactorily, you'll redo this, including a basic host system for the conformal symmetry. Okay, so there will be not just C's, the analog of C's will be not just for diffeomorphism, but there will be a C for while. So there will be C mu's, which for the diffeomorphism, and a C tilde for while. Okay, and the corresponding B's will also have 3 components, because it will be a B mu nu without being traceless. This would be the most satisfactory thing to do in the beginning. Okay, so how many fields would you have? You would have this B mu nu field, so 3 components, and then you will have a 3-component fermionic B mu nu, 2-component fermionic C mu, and a 1-component fermionic C tilde. So 6 components of fermionic fields. Okay, and this Lagrange multiplier field. Then for that you work out the algebra of the symmetries. The algebra of the Weil symmetry is very simple, because Weil transformation acts only on the metric. It's an abelian symmetry. You phase you multiply the metric by some overall factor, you multiply by another overall factor. It's a very simple symmetry. Okay? Because it's so simple, that part will be totally trivial. Anyway, so the most satisfying thing would be to do that and to work it out by then integrating out this B mu nu. Okay? And the part from the Weil symmetry, the cohomology of the Weil symmetry will be something totally trivial. So anyway, I'm just going to leave you to do that as an exercise. There are 2 things you could do. You could either first integrate out the Weil part and do the hosts business, the cohomology analysis for having integrated out the Weil part, or you could do it before and you can compare the 2. Finally though, you're going to integrate out all modes including the Weil, also integrate out this B mu nu, and get something that's the analog of just this. Right? A BRST symmetry where the only fields are X, B and C, where B is traceless and C is, B is traceless and C is an arbitrary field. Is this clear? I'll just say it once again. I'm going to say, so you have this action with 6 fermionic fields and these 3 bosonic fields B. Okay? Now, you could take the action to integrate out this capital B mu nu. So you get some complicated BRST symmetry transformation rules for that. That is the most satisfying thing. It's most complete, logically complete. Now, like we did before for the point particle, you can integrate out this capital B mu nu, and you can also integrate out the C tilde and the trace component of B. You see, the reason all these are easy to integrate out is they don't couple to derivatives. Whenever you've got modes in a path integral that don't couple to derivatives, integrating them out produces algebraic equations. Okay? So it gives you something that's local. So these you can just integrate out. Then follow what we did. Use the equations of motion for these modes to substitute into the BRST transformation properties wherever wherever they appeared. Okay? And in doing that, you will get the analog of this thing. Okay? It's a long procedure, And I'm not going to go through it in class. I'm going to urge you to repeat. Conceptually, there's nothing beyond what we did. Okay? Once again, you'll for the diffeomorphisms, you'll have to carefully figure out what the F, alpha, beta, gammas are. Okay? You just have to go through the same exercise. There are a few more indices. It's more complicated to go through. But the final result I'm claiming is the following. Delta x mu is equal to I epsilon C del plus C tilde del tilde on x mu. Pretty satisfying, right? Pretty near to this was C d by dt. Okay? C was a little infinitesimal vector field. This is, of course, what you would get under diffeomorphisms, where C was the infinitesimal diffeomorphism. So this part was obvious.
I'm sorry, what's the tilde part? The tilde part
Is bar. C bar del bar.
Okay.
Right? This is the analytic part of the.
Yeah.
Yeah. So this is obvious. Okay. The other part is also sort of obvious. It's del C is equal to I epsilon. Yeah, exactly. I epsilon C del plus C bar d bar of C. And there's a similar for C tilde, C bar, del C bar, which is equal to I epsilon C del plus C bar d bar of C bar. What? Now there's the del B. The del B is, of course, the interesting guy. This is the guy that turned out to be this chap. Now, this del B is the interesting guy, and it has a lovely form. It's I epsilon Tx plus Tg, where T is the stress tensor. Hamiltonian, now that becomes the stress tensor. And last time it was Hamiltonian was the matter plus a ghost, though you didn't really care about the ghost part because that Hamiltonian was 0. Okay? But now this is some local quantity. You get the stress tensor of the ghosts, and that's not 0. Okay? And of course, dB bar is equal to I epsilon T bar x plus T bar ghost on B bar. On B bar. Yeah.
So the first one.
Oh, sorry, no, not on B bar. It's just what it is. Sorry. Just. It's going to be related to the fact that the equation of motion that has not been imposed by going to metric equals eta is that T has to vanish. That is the point. And this is actually a general structural feature of this BRST thing. That if you go to a gauge where you've completely fixed gauge, okay, then the BRST thing will be sort of trivial. I don't know if you've ever worked with, let's say, Coulomb gauge in electromagnetism. Yeah, just basically trivial. The ghost sectors are more or less trivial. The whole BRST analysis is more or less trivial. What you get, where you have non-triviality is where some gauge fixing has been left over. And then there is a corresponding equation of motion that has to be imposed. And this is a very general thing that happens all the time. So it's not at all a surprise, but you can go through this and check it in detail. Okay?
What is this test? Sometimes you do not gauge fix everything, still your propagator becomes non-singular.
No, it can never happen if you do not gauge fix everything, that your propagator will be non-singular, because then you could, the motion that is pure gauge.
So that's like in Chern-Simons.
Yeah, it may be that that singularity is an integrable singularity. Like in Chern-Simons we get 1 over p minus. So modes with p minus equals 0 have singular propagator. And those are exactly the modes that we've not gauge fixed.
Should not be non-singular, but he says that it might be that he may still go through with it.
It might be that it has no effect. That's now an issue of detail. But if you have completely gauge fixed,
Then it will be non-singular.
then it's non-singular, exactly. Exactly, these are related terms. Okay. 10 minutes more and I'll let you guys go. Okay, I'm sorry. On a holiday to keep you this way. Okay. Fine. Okay, so I'm going to leave the derivation of this starting logically. Logical presentation, logical derivation of this as an exercise, guys. I urge you to do this exercise. Once in your life you should do it.
We have seen the while part completely, is it? While part is completely fixed.
While part is completely fixed.
So the tracelessness function, this function is traceless.
B is traceless.
Okay, so therefore this is not okay.
Yeah. The while part, well, you know, the part that is unfixed is this combination of diffeomorphisms and whiles is conformal transformations.
Yes.
Right? Locally, conformal transformations are analytic things. Okay? And that's why this corresponds to the fact that locally there are analytic equations left in pose. These T equations. Okay, these things always go together. Okay. Now what we're going to do is to take these rules and try to understand how to implement them. Okay. Oh, by the way, there are two exercises I would like you guys to do. The first exercise is to use the logical derivation to check this. The second exercise is to take the gauge fix form of the string action, matter action and Boost action, and check that these transformations generate a symmetry of that action, like we did for the point particle. Okay? So, just to check all signs and so on. Okay? It's the same kind of exercise that we did for the point particles, a little more work, not going to go through it. Unless somebody comes and says they're having trouble, then we can go through. Okay. Now, something you notice here is that there's this beautiful analytic structure, right? The things could decompose into analytic plus anti-analytic. This part is analytic, this part is anti-analytic. Okay, so you could wonder about the following. You could wonder, is there a BRST current, okay, that is analytic, okay, that generates these transformations? A BRST current such that the analytic part is analytic, the anti-analytic part is anti-analytic, okay, and whose OPs with the corresponding operators generate these transformations. That's the last thing we'll talk about today. Okay, so I'm claiming that this works and then we'll check it. Consider JBRST to be the following. JB, I'm writing just the analytic part. So this is a current with analytic and non-analytic parts. Okay, often in what we did previously, like for instance, TZs, anyway, often in what we did previously, we would have only a current whose component was purely analytic. Okay, here we're looking at a charge which has both analytic and anti-analytic part, but the analytic part is analytic, the anti-analytic part is anti-analytic, so it's conserved. Last time meaning the point particle?
Yes.
The point particle, there was no current, of course, it was just a charge.
What might
It was c times h.
sorry.
Yeah.
C times A. So now it is going to be C times T plus T.
Something like that, but there's going to be some factors. Yeah. Yeah. So there's, consider c times t matter plus half of c times t ghost plus 3 by 2 del squared c. Okay, this last term has been put in order to make this thing a tensor. This term is a total derivative and will have no impact when we integrate totally. Okay, so all we have here is knowledge of the BRST charge. Current is of course ambiguous up to total derivatives. Okay, we're free to put whatever total derivative we want to make something nice. This thing will make something nice. That's why we put it. The last term was not, it was just to make something nice. Yeah, it's just something to put to, you know, to make the formula more pleasant. That's no. Okay, now I'm going to remind you of the yeah. We will write down an explicit formula for this JB, and for that we need an explicit formula for the stress tensor of the BC system. I'll just get that right. It was basically del B times C plus minus lambda times del BC, but I'll get that. Get the coefficients right. Del BC minus lambda del BC, and lambda was 2. So this TG was del BC minus 2 del of BC. Everywhere, by the way, everything's normal, conformal and normal order. Okay, I'm not writing that, but that's always understood. Okay, so let's work this out in more detail. This is JB is equal to C times T matter. T matter, of course, we know, right? Okay, I'll write that down later. But this thing, let's put in explicitly, plus half times del BC, C del BC, minus 2 del of BC times C. Okay, now let's open it out. Plus 3 by 2 del square C. Okay, so if we open this guy out, this is what?
Why JB was not a tensor? It was not tensor because of this anomalies?
We'll see. We're going to compute the.
But it's precisely, is it because of this presence of anomalies it was not a tensor?
Which anomalies? Like D minus 26, that kind of thing?
It is D minus 26, but those anomalies, this wild anomalies that are, why is it not tensor? You are going to calculate stress tensor and JBOP, right?
We'll compute stress tensor JBOP, and we'll see that this term will be needed to make some, I don't know, 1 by z squared term or something like that.
Had it been this, suppose this is a new theory, in which you have T matter and T ghost, and both the theories have C equal to 0. So stress tensor OP
Right.
is 0. That does not have any anomaly. If it was like that, then would it be that you don't need this term?
Say that again. If you had what?
Let me say.
Yes.
Say you have a theory in which your JB is C times Tn, the
Same structure.
And last time I don't know what that is.
Yes.
I am not adding that.
Yes.
I want to calculate stress tensor JB OP.
Yes.
And I want to check if JB transforms like a tensor or not.
Yes.
Now, if I supply you this information,
Yes.
that the stress tensor OP does not have this C term. So you had an anomalous term C in C stress tensor
C means central charge.
yes, sorry, central charge.
Yes.
So let's say this term is not there.
Uh-huh.
And then if you calculate the OP, would you see that the JV transforms like a tensor?
I don't even, we'll check it, but I don't think so. You see, the tensor, the non-tensorial part is purely in the ghost vector. And comes from the fact that C also belongs to the, you know.
Ghost vector also has this problem, right? Ghost vector also has this non-trivial central charge.
Exactly. So that's minus 26, let's say.
Yes, so if both of the terms does not have any central term, you understand, no central charge in any of the theories, then is it going to be that JV is a tensor? I'm just trying to understand why this term is there.
Well, let's see. You know, you could have you'll have a term. Let's see. We're going to do the calculation in just a minute. But let's see what kind of term. Okay, let's look. What kind of term does this give you? You see in the TCOP, in the TJBOP, this term, the extra term, gives you T with C.
Yes.
Now T with C is C. So let's see what the extra term is. Okay. So the extra term will be 3 by 2 del squared, and then what you get with T acting on C. So suppose we have T at Z1 and C at Z2. Okay. So then we'll have C at Z2 divided by Z12, the whole thing square with a minus 1 because C is weight minus 1. Okay. Plus del 2 of C of Z2 by Z12, and then you have to take two derivatives of this. Okay. And all the bad terms are coming because there's this extra C business. Now, okay, maybe what you're saying is right. So let's see. So what you're saying is that these are the bad terms because you want to compare this to what you get from the TTOP with the minus 26, right? Some alpha, let's say. Some alpha by 2.
The point is that if all the stress tensors are transforming like a tensor, if you have two tensors which are tensors, then their addition is a tensor. All I'm trying to say is this. But now, one of them is a tensor because of this bad guy.
Yeah, you're probably right.
Because of the bad guy, so it must be that this.
You're probably right. You're probably right. But this part of course is irrelevant. So it's just this times this. Or maybe even this actually, because that's the C part. Yeah.
So all I am saying is that if everything was a tensor, how could that addition?
I agree with you. I agree with you. That had it not been that the T's had this funny transformation, then this would be a nice quantity. In fact, we will see that this is not, even with this addition, this is not exactly a primary field.
Unless you said something.
No, even when we said it's not exactly a primary. It will not. It just cures some of the terms in that OP. It just makes that OP a little better. Okay, but I agree that had these been genuine primaries, then products of primaries with primaries, and had there been no cross singularities. I mean, actually, even that is not totally clear, because there could be new singularities.
Between matter and ghost, you are saying?
Between, let's say, the ghost and the ghost. Give me a minute. No, you're probably right. Actually, it's not so clear. You see, it's not like that. It's because of conformal normal ordering. It's not totally clear to me. Yeah. Because of the normal ordering. You see, it's not really like the product of this and this. Because
it's not really product, it's something more.
yes. and that might give you something extra. Had it been classical, of course, what you're saying is right. It's not 100% clear to me. Okay. Yeah. For instance, you know, del x. Yeah, let's.
Just prove it without using, but then you say norm, how would you define normal ordering in
Yeah. Del x, let's take a free boson theory. Del x is a primary. But del x is not a primary.
Yeah.
So this was an example. It's the stress tensor, right? It's a descendant of identity.
Your primary is slightly little bit more.
No, but you wouldn't the
Quasi-prime, I am going about quasi-prime. Primary is little bit more.
but the logic of your argument would have worked also for primaries. Because primary times primary will transform the same way. Because it's just, you know, the factor of del f by del z prime by del z to the power delta. Classically, had you multiplied one primary with another primary,
It might not be a primary. I am saying it might not
I just don't understand where in your logic primary is distinguished from quasi-primary.
all I am using the tensor structure. I will not, JB might not be a primary.
But I,
Okay, let's just go.
yeah, you gave us an argument for it. If naive application for that argument would suggest product of two primaries is a primary, is what I'm saying. So I'm.
Because the normal ordering will create issues with that idea.
So it might also create issues with other things. I mean, it's just that the argument I don't believe. So I'm not. Okay. Yeah.
Yes, I agree that normal ordering will screw up that.
Yeah.
Try to screw up that.
Yeah. Okay. Not at all. Okay. Now let's look at this object here. So this is plus half. So let's say minus. Now this quantity here is C del BC. C del BC is, you know, with the normal ordering is just 0.
Yeah.
Because you can bring the C to the C, and that's 0. Okay. Similarly, when you open this out, the place where this del hits the B is 0. The only thing that's non-zero is the place where the
C
del C. So this is equal to CTM plus, now half kills the 2, and we'll pull C and del C out. So C del CB plus 3 by 2 del squared C. Yeah, Pulchinski writes it as with a B here, takes it to 3 of them, so that's the same. To 2 of them, so that's the same. Okay. So claim this quantity, this JB, is the current that generates these transformations. This and of course the corresponding and non-analytic part. So what do we have to prove to check that this is indeed the case? What we have to prove, what we have to do is to compute the OP of this current with each of those fields and check that what appears on the right hand side here is the coefficient of the pole.
And for free particles, this JB was some tensor for free particles.
For the free particles, now there wasn't even a notion of a tensor.
M square is 0.
No, what does a tensor even mean then?
Said M square equal to 0. If you said M square equal to 0 with free particles,
Mm-hmm.
anything about transformation on the diffeomorphism.
Under diffeomorphism.
I was like, this, you added this term newly, right? That is the problem. Is there any analog of this in point particle?
No, I don't think there's an analog, but also this term has no physics in it, you know. It's just all we care about physically is the BRST charge. This thing doesn't contribute to that charge.
It is not going to contribute.
Yeah, so, you know, if you don't like this, don't work with it.
If we drop it, still
Everything will go through.
Okay.
It doesn't matter. We don't. It's just a convenience to make formulas a bit nicer.
Let's forget this.
Yeah. It's just put it by hand because you can, and something. The formulas look a bit smaller. That's all.
Okay.
Okay? So what we want to do is to compute the stress, the OP of this with these three fields and check what happens. Okay, so now we'll quickly do this and then we'll stop today's lecture. Okay, so now we need to remember various things. First, we need to remember the formula for the the matter stress tensor. Now, if somebody has that in their notes, otherwise I'll pull it out of Pulchinski. Minus 1 by alpha del alpha. What was it? Finding formulas in Pulchinski remarkably hard. Minus 1 by alpha del x. And the second thing we have to remember was what the OP was. So the OP was x, xz, x0, w was equal to minus, was it alpha log of z minus w, the whole thing square. I'll check that also. Minus alpha by 2. And of course, x mu. And then continue with our lives. Okay, so let's first do the calculation with x mu. So the only part that contributes to the x mu part is CTM. So we have C of z, T, Tm, so that was minus 1 by alpha del x at z, acting on x mu at 0. Okay, so what can we do? What we could do is to take one of these. We contract one of these. There's a choice of 2. So we get a minus 2 by alpha. Let's say I've chosen this guy. So that's C of z, del x of z. And then I get del x of z, x mu at 0. So I use this formula. There's minus alpha by 2. And then we differentiate. So there is a 1 by z. Okay. So minus alpha by 2, minus alpha by 2, and 1 by z1 to z 1 by z. Okay, so 2 by alpha minus 2 by alpha cancels. Since this is 1 by z, these can be replaced by 0. So this is equal to C of 0 del x of 0 by z, and that matches this C del x of z. This part will come from the anti-angularity part. The 1 by z residue is that. Okay, let's look at the next guy. So, no, not even a factor of 2, right? The 2 cancelled.
There's another C0 del x0 over 2.
No, that's over z.
Oh, yeah, I'm sorry. My bad, sorry.
Not at all. Okay, so if you're happy with this algebra, I'm rubbing it out, and then we'll do the algebra for BRST charge on the C host. Okay, all good? Now let's use this form of the formula. BC del C plus 3 by 2 del squared. BC del C all at z plus 3 by 2 del squared C at z acting on C of 0. What we should expect is this business. Sorry, this business. Okay, remember this guy is conformally normal ordered. So the only thing that we can get is the B acting on C. Now B we put to the left, but because there are two C's on the right of it, we can as well put it to the right. And so we'll get 1 by Z. So we get C del C. And here, from here we get nothing because there's no B. Okay, so C del C both at Z, but since they're at Z, the only singularity is 1 by Z. That's at 0. So by Z. And that's this C del C. C del C. Once again, the other term will come from the anti-analytic. The last term and the most non-trivial of the lot is this guy. Okay? So for that guy, what we need to do is to take, we need both terms. Let's first do the matter part, and then we'll do the oh well, let's start. So the CTM. But there's also a C. That has to be written. Exactly. Exactly. So but first let's just do the matter part. CT matter acting on B. Okay. Now here we don't even need to open out the T matter because it's just C acting on B. So that's clearly T matter at 0. It was actually at Z, but only 1 by Z. So this part works out right. And then we want the T ghost part. So we could do it like Indranil wants, or we could just do it directly, whichever way. I'm just going to do it directly, just whatever. Okay, so now there is BC del C plus 3 by 2 del square C. First, let's look at the BC del C. The 3 by 2 del square C, what will it give?
Something 1 over Z cube.
Yeah, it will not contribute.
Yeah.
We'll check that. But let's look at the BC del C. It should not. Yeah. So let's first look at the BC del C. So the BC del C part gives what? BC del C with B. Now we need to contract the two C's. Okay. So let's contract this guy first. So that is a minus 1 by Z square because 1 by Z and then its derivative. What? Del C with B contracts. Fine, but that's CB, that's 1 by Z, and derivative
now
of that.
Now we'll Taylor expand the other BC.
Yeah, so that's B of Z, C of Z. Right. Okay. Plus, there's the C part. Now that contributes. Now why did I put a minus here? Because of the derivative, yes. Now the C part already has a minus because you. So that's B del C both at Z, but now we only get a 1. So this is just at 0. Okay. So I'm clearing, we'll keep this formula. Clear the rest. Okay, so now we need to Taylor expand this. So in Taylor expanding, we can get the derivative either from here or from here. So the final answer is minus del B C minus B del C minus B del C. Okay?
Yes, and which is just the TG. Or
yeah, now TG I have to write again. Let's first combine it and then we'll check. So minus del BC
minus 2B del C.
Minus 2B del C. Yeah, so that's good. So that's minus of del of BC.
Yeah.
Minus of del of BC minus B del C. Okay. What we expected was del BC minus 2 del of BC. Now presumably this is this. Okay. presumably this is the same thing.
Yeah.
Same thing.
Same thing, yes.
Okay, so that's
Second term total derivative, that is the total derivative, the second one.
the second one. Yeah, yeah, yeah,
Then it becomes 2 of the first one.
yeah, exactly.
And the
And the remaining sign is exactly, exactly. Good. So we've got this TG as well. Last thing we want to check just explicitly, and then we will stop, is that the del square C term does not contribute. So 3 by del square C doesn't contribute. 3 by 2 del square C will also not contribute. So let's check that. Okay. So that's B C del C acting on del square C. Okay. So that is,
It's del square C acting on. Sorry.
this was the BRST charge, the part of the BRST charge,
Yes.
and of course, sorry, what am I saying?
Yeah, del
You're
square
right.
C acting on B.
You're right. Sorry, del square C acting on B,
Hmm.
and now it's obvious because it's del squared of 1 by z.
Yes.
So it's purely 1 by z cubed.
Yeah,
There's
that's-
no numerator to Taylor expand, so it doesn't contribute to the pole. Okay, so we verified that this transformation law is generated by this current, the charge corresponding to this current. So once you agree that this transformation law is correct, we have checked that this is a current that produces the right BRST transformation. Okay, if you give me like 3 minutes more, we'll just do the OP between this and the stress tensor so that we clear up in the so that ends that discussion. And then we'll turn to everything else. Okay. What's for lunch? What is the situation with lunch today? Is East Canteen
East
open?
Canteen open.
And will they shut very soon?
I think maybe around 2.
Around 2? Okay, so we can take 5 minutes more. Right?
And Jagadish Canteen
Will also be open. Okay. So the last thing I want to do is to compute the OP between the stress tensor and okay, it's going to be a bit of. Why don't we do it next time? Let's do it next time. It might take 5-10 minutes. Okay, so I'll just give you the result. I'll give you the result, but we'll do it next time just to see what difference the del squared C term made. But I'll just quote Polchinski's algebra for it, and famous T of z times j BRST of 0 oh, so actually when Cm is 26, it is a 10. It's a genuine tensor. I've forgotten that. Yeah. So this plus j BRST by z squared plus del JB by z. I'd forgotten actually with this. Okay, so that's quite nice. Maybe it was necessary. Maybe it was necessary. Okay, this is one of the things we will check next class. Oh, let me just also write down the other thing that we will check. That will be very important. We will also check that j BRST at z, j BRST at 0 is equal to Cm minus 18, 18, right, by 2z z cube into C del C plus Cm minus so minus of Cm minus 18 by 4z cube, so z squared, C del square C. Minus of, and this is the really important part, minus Cm minus 26 times C del cube C. Now, why is this important? These two terms are whatever they are. However, this term tells you what? QBRST square is. Okay? So this term tells you that the BRST operator squares to 0. Okay? If and only if C is equal to 26. So this is a crucial piece of algebra. Okay? Once we understand both these things, we'll be in business. We have all the formal properties, and then we will prove the no-goes there. I will compute the BRST cohomology for you in the Hilbert space of the string, and show you that we get the same thing that we got with our light cone quantization. Okay? And that will also tell us, answer the question we started this discussion with, namely, what are the things that we should put into the string scattering amplitude formula? It's of course any state in BRST cohomology, but there's a canonical sort of basis